start in the initial state, then you make A, then you make a B, then you make a C, and then you start again. So a sequence of ABCs. And so what is the behavior of this computer? It is this sequence, A, B, C, and then A second time, B second time, etc. I'm sure you understand what it means. Now we have again the red one, and it has the behavior DEF. Likewise, triple. What is its behavior? It is this. Okay? And now we make, say, a virtual thing. Now in our mind, we say, let's consider the two computers as one system. Okay? I don't change anything on the physical structure. I only in my head say, I consider this as one system. Now the question is, what is the behavior of this system? Okay? So what is the behavior of the system? Of course it can behave like the blue one, but still this is debatable, because if it behaves like the blue one, so if it behaves like this sequence, then you can complain that suddenly the red one doesn't do anything. But that was not intended. The intention was the red one does this, the blue one does this. So this infinite sequence alone is not what we would like to have. Okay, of course, you know, instead of starting of doing only this circle, you can also initially start with the D and then do the blue circle. Or you can also continue with E and then do the blue circle, and then you can alternatively have this red circle, and you can also only start the red circle initially, but also do it here. And that is considered to be the behavior of the system. Isn't it strange that we didn't change physics? We only in our mind say this is one system. That's what we want to have. And formally, suddenly we have this kind of thing. And if you look at all the behaviors of it, suddenly we say it has very many different behaviors. For instance, first an A, then a D, then an E, etc. So we have infinitely many different behaviors in this model. And even more, we need an assumption of fairness, that is to avoid that after some time only the blue one does something and the red one does nothing. Or only the red one proceeds and the blue one does nothing. So suddenly we have amazing difficulties. These fairness assumptions are not at all trivial, they are not implementable with something. So and what we wanted was very simple, conceptually to conceive two independent systems as one system, that's all. And we got an amazing difficulty. And this cannot be the solution of our problem. So if you try to model, say, the internet in this way, you have to assume now the internet is in a certain state, and now I click on my computer, and now the internet swapped to another state. I think this is not really convincing. And the problem here is that we assume global states. So the assumption of global states is nonsense. With global states, this is a virtual thing which does not give you any interesting information. So how can we improve the situation? Well, and even more, this model is usually motivated by observation. That's what they say. They say, you stand beside the system and then you can see what is going on. And we see the events occurring in some order. And maybe two events occur at the same time, but it doesn't help. All this does not help. And now we do something else. We say, let's assume technically or formally this as one system. This is one system. So is there a system model in the world that conceives this as one system? There is one, and I'll show you some of you may know it. You just make boxes around the steps here, and then you put some black dots here, and then you have what is called a patronet. This thing is very large, you should clap. Consists of two separate parts. But that is not the essence of the story. The essence of the story is what is the behavior of this patronet. And now we will be surprised. This is the behavior of the patronet. What is this? It's a partial order of event occurrences. So these are ordered and these are also ordered, and between them there is no order. And to understand this even better, we want to make a variant of this. We want to say the each occurrence of B should be before the each occurrence of F. So they say the blue may run as quick as it wants, and the red one must be synchronized with the blue one. run. The red one should not run very quickly. So how can we express this as actually very simple like this? So each time the B occurs, there's a total here, and there can never be more F's than B. And then the behavior of all this is that. So the first B is before the first F, the second B is before the second F, etc. And now you see, it's a partial order of event occurrences, and that's how to say. It is one behavior. It's a deterministic system. There is no choice, no alternatives in the system. So anyway, expect one behavior, and you have here one behavior, one run, one execution. So the mistakes done so far is that everybody assumes a single behavior is a totally ordered set of event occurrences. Why should it be totally ordered? The word is not totally ordered. The word is partially ordered. And I give another example that I learned about only on last Monday. That is this beer hall pattern. And I also read in the internet and it says this beer hall pattern is so that people are continuously crisscrossing from one another. So you have a beer hall and the people meet one another and they click, I say again, and for the social done in Bavaria, they click their glasses. So I have a glass of beer and then I go to Christoph and we click our glasses and then we click. So everybody goes around and clicks with other people with their glasses. The question is, how can we model this? Okay. So now I don't model the system, I will show you how to model, say, a single behavior in this context. For instance, this one, there's a red person and a green person, and you see, they meet twice. They click here their glasses, and after a while they click again their glasses. So they click two glasses, and you have two other behaviors with the black and the brown one. They only click once their glass. Okay? And you have a blue one. He clicks first his glass with the black, and then with the brown, and then with the green. Okay, this is the structure of the behaviors here. So what would it be mathematically? Well, very simple. There are these clicking behaviors, so we have A, B, C, D, E, F. These are clicks of glasses, and together they constitute again a partial order of events. Okay? So the world is very naturally ordered, not totally, but partially. That's the whole story to say. And if we keep this in our mind, that this total order of events, which was so fundamental for the computer science, is simply stupid. So this kind of behavior is much more natural. The world is partially ordered and not totally ordered. Okay? And we should avoid this naive notion of time that is not ordered in time. For instance, you can say, okay, these events are independent of each other. But are they at the same time? Well, not necessarily. The time is irrelevant because you could say independence does not mean the same time because A is independent from B and B is independent from B, but A is definitely before B. So to be at the same time is intuitively a transitive relation. But in unorder, so causal unorder is not a transitive relation. Okay. That's all I wanted to say about the first topic. Now we come to the idea, to some concept of a theory of services. And this is maybe the most important slide now. So if you have been sleeping so far, please wake up. So first again, I speak about classical programming. Then you have languages, you have implementations, and I have written two languages, and I don't speak about implementations. We have something else, namely concepts. And there theoretical informatics goes in. So we want to speak about the fact that termination of a Java program is not decidable. If you have a Java program and an input and you want to know will it stop or not, don't start to program this, but think a little bit and say there is no program. It's not decidable. You want to speak about the fact that one big while loop suffices. You don't need very many while loop. One while loop is in principle enough. You want to speak about algorithms independent of programming languages. Okay? So Euclid algorithm is an algorithm that was invented before programming languages existed. And I fear that computer science people sometimes cannot think anymore about algorithms without thinking about programs. It's a big stupidity, a big mistake. So algorithms has nothing to do with programs. Okay? It's not that point. You want to speak about semantics of programming languages, you want to speak about verification, and all this here, that is mathematics. And languages is not mathematics. Okay? Fine. What is the situation in the world of service-oriented computing? We have languages, we have implementations, and I must admit this list I learned on Monday by Jorge Nati gave a wonderful list of implementations. That's what we have. And what about the concept notions? Well, what we need is to speak about that of life, of simulation, of function, equivalence, instantiation, correctness. You can do much more of this. But we should speak on about these concepts here, where we have mathematics. Do we do this? No. Here we have a big hole. We don't do anything. Instead, we do it in this relationship. And I think this is one of the biggest mistakes. If we speak about these notions, we do it in plain English. And if you look at books about service orientation, they always have two parts. First part says service orientation is an implementation and language-independent concept. And then they, in plain English, explain something. And the second part, there's a language. Okay? But there is not a formal mathematical representation of what it is. And how can we assure that something, an algorithm in the service-oriented world is correct? We cannot speak about the algorithm because we don't have mathematics. Okay? So instead, and now I understand why standards are so important. Because standards somehow try to solve this problem. With a standard, you have an intuition that everybody thinks to mean that they have the same idea about something without making it fixed in mathematics, but standards help a little bit. And now I only understood the term technical neutrality, which was so virulent around on Monday by your cleaner again. So I think it was excellent that we have chosen your cleaner. I have learned a lot from his talk, and I put it right into this one. Okay. So technical neutrality means that the language is independent from the implementation. Now let's look into this word. When was this a problem? It was that we have a language independent of implementations. It was in the late 1950s that they had the problem, and then they have solved it. So in computer science, they have solved problems in the late 1950s, and now in the service-oriented world, we are in a situation where the others have been 50 years ago. That's the plain truth. Christoph doesn't like it.
No.
Okay. Of course, this is my central provocation of the day.
And you have already the solution, that's even worse.
No, my point is that people are so ignorant, nobody pays us for that. They all want to have some implementations that don't function. And why don't they function? Because we don't think about this kind of things in mathematical terms. Okay? So what we should have is an analogy to programming language. The semantics of a service is a mathematical object. That's our goal. And so far it is not. And almost nobody cares. You are laughing all the time. I like that. You seems to agree with me. I'm the only one here. Okay. It is presently not the case, but we should spend effort on this. And we don't. Okay.
But Wolfgang, you say that there doesn't seem to be hope. I don't believe you.
There is no hope.
Yeah?
But I want to provoke hope.
Okay. I thought you know already the answer.
I don't know the answer. I will show you a little bit what might be towards the answer. But there is not a simple answer. Okay. So what we could think about is a generic modeling language. So something like the tool machine of distributed and non-ending and etc. How would it look like? Just one idea what one could do. You look at all modeling languages for all services. You look at their expressive power, you look what they all do, and then you take the intersection of them. That is, what do they all have in common? That seems to be the center of service orientation. That would be a verse to try to do it. And what is certainly not the solution is certainly not BPMN. BPMN has 402 different concepts. So isn't that crazy? is not listening.
I'm listening. And it's not 400, but it's okay.
402 different concepts.
How do you know this number?
I've counted it out. You can do it with some multiplication.
Ah.
Okay, you don't have to count until 400. Okay.
So why did you take the intersection of the union?
But if you have a concept that is present in all specification languages, then it is relevant. If it's
Relevance is something different from being expressive.
No, I don't want to have the most expressive language, but the most fundamental one, which includes only notion that you need in every context, in every specification. Okay, that is something that is not syntax dependent, or some aspect that only is relevant in one language and not the other. Okay? Yeah. So what kind of thing do we require? We know we need an elementary notion of composition. And composition should be a simple mathematical or logical operation. So far it's a technical something on languages, but if we have mathematics for services, then composition should be simple. If it's not simple, the fundamental stuff should be simple. Okay? If they are not simple, we will never get a decency. And one point, of course, is if you have two services and you compose them, then the result should be again a service, right? The word of services. But frequently, if you compose them, they don't interact. The composed thing does not interact anymore. Then it's a special case, but still it is a service. But ticketing is you sell a ticket, or somebody else buys some other service, buys a ticket, and you compose them, and then this is a closed system. But this is a special case of a service. Okay? So we start now with an algebraic structure, saying, aha, we have a set of service, a set of something called services, we have a composition operator, and that's already a little bit of an algebra. We extend it afterwards, but this is starting point.
This is all again a partial function, right? The composition operator. The composition operator is partial.
No, good question. I want it to be total, in the sense I want what I want. Okay, you want something else.
Yes, it's fair.
So what I want to have, whenever you have two services, you can compose them, and the result is a service.
But maybe a non-functional service, because it can't work.
Of course, I would like to express what you say, but that should later on come as a refinement of that.
Okay.
Okay? Or later on you can include this and that. So what I would like only to say is, these should be the fundamentals to start with. And what you want to express, don't start with everything in the first minute. It should be possible to put it on, slowly, to put it on top of the rest. So this is algebraic structure, and I will later on come to this.
Wolfgang, if it's algebraic structure, what are the rules of computation? Is it associative and so on, blah, blah, blah?
Don't be so impatient. You can later on impose rules on it. I only want to give you, and I finished today with some fundamental requirements on composition. And then you can come and say, I want a system where this and that is on top of this. So I hope that what I tell you is so fundamental that you can everything you wish put on top of.
Yeah.
Okay? So I don't say you don't need it, of course you need it for this one, but you don't start with this. You start with some elementary stuff. Okay. So I started a bit with the models, or with the graphical representation. So there is a transition system that is just a system where you can have steps, sequences or partial order steps, and there are some channels, they are called channels or an interface, that something goes in and out, and of course we want asynchronous communication with an environment. So that is the structure of services. The service communicates with its environment. That's all. And now we can ask, what is the semantics of a service? Well, during computation, there's something going in and out of channels. That is the fundamental idea. And so one could mathematically start saying the semantics of a service is a relation on the streams that go in and out. That has been done. And this can be done mathematically, but it makes no fun. it is technically extremely not intuitive, and so it is not too convincing what has been done there. And I give you a completely different alternative to that, which I hope you will have. So how compose them? Again, you have now here two services, and you see it's not by chance that there are two channels with the same symbol in the B. So you glue these two things together, and the resulting service S composed of T is this one, which has now a dual interface in the A and B and C and E are in U. What's the point? Right. And the composed thing is a service again. It's a box, something inside, and an interface. The world consists of composed services, and some starting trivial services are elementary services, and you can compose them as long as you wish. Okay, in addition to just doing this, you want to accomplish something. The service should be useful and should do something with it. So we have requirements to services where you can ask, does this service fulfill this requirement, yes or no? Or else you can say, is it the case that S and T communicate boundedly? That means that not on one channel you have unboundedly many symbols, or many messages communicating, so there are more and more messages around. Or is there a limit? You have no more than, say, seven messages on the B channel. So bound or unbound. Or do they communicate responsibly? That means there is not a case that after a while one of the services doesn't do anything anymore. So a lot of questions. If you have target states, if you have say, goals, then you can ask, do they together neatly terminate or strongly terminate? Or is it deadlock free? Is it lifelock free? I don't go into the details of those notions. There are many of these notions that you can ask for, and you can formulate them as logical formulas, and there's a logic called CTL star, any kind of temporal logic that is fitting to this kind of things. And I don't go into all these details. The central point here is that if you have a requirement on services, then you can define what it means that two services are partners with respect to this requirement. Namely, two services are nice, or they are partners, if the following is true. When you compose them, then the resulting service is nice. That's the search problem. For instance, if they together come to an end, and if the requirement is that the service should come to an end, then they are partners with respect to this problem. Okay? So given the property, you have the set of partners. Or for instance, the question, can I substitute a given service S, can I replace it by T? So wherever S is, instead of S, I use T. You can define this and you say, well, you can replace S by T if for all other services use the following rules. In case S together with the U fulfills the property, then also T together with the U should fulfill the property. Okay. And the standard example here is if you have a coffee machine, can you replace the coffee machine by another machine that serves coffee and tea? Okay, of course you can do it because the old usage only for coffee can still be served. Okay, so a lot of things can be done, and also on the fly substitution, that is fundamental in services. In long-running services, you want to replace one service when it's already running by another service. A very surprising thing that is in classical theory not addressable well. Or you can define what an adapter is. So assume you have S and T, and you want to propose S and T, but it does not fulfill the requirement you have. However, if you have a third service called adapter, the U, if you want the adapter here, and maybe that together they fulfill the property phi, then U is an adapter for S and T with respect to this property.
Is the assumption that S and T would not imply rho before?
But if they imply rho before, the adapter can be trivial.
Okay. Yeah.
You can do it, but it makes not much fun. Okay, so now we can start already a lot of interesting questions. remember how few assumptions we did. Only composition and requirements, nothing else. So you can ask, does S have partners for this requirement at all? That's the notion of controllability. Is T a partner of S? Is there a most interesting, most canonical, most simple, most whatever partner? So this kind of question you can ask, and the operating guideline which Frank likes so much, how can we characterize all partners of a certain service? Okay, these are fundamental questions, and now giving some concrete notion of whatever you can decide them or not, and you can start to make a mathematics out of it. So the general goal is the description of semantics and particular composition of services on a high level of business logic. We don't want to go into details. And for instance,
what is high level here? You are using terms now.
Okay. Abstract level. Abstract.
Okay.
This refers, no, it refers to some. I just skip this slide. Okay, I take this slide. So let's go again to the algebraic structure of services. So given the set of services, we know we have a composition operator, but now in addition we also have a set of requirements which are, say, predicates on the set of services, and now the structure is a little bit greater. But still it's a very nice algebra. One binary operator, a set of numerals.
So the requirements are not part of the services, right?
Huh?
The mathematical notation is certain. Row 1 to row n is not the subset of S, isn't it?
No, not at all.
Yeah, but you have written it. It's only minor typo.
Okay. You can conceive a property of a set as a subset, namely all those elements where the property holds. That's what logicians do always, but I'm sorry I have done it. Okay? You can say the prime numbers are a subset of all numbers, or 2D prime is a subset of all numbers. In this sense, I saw it. Okay. So now again, I said already T is a partner if the composed system fulfills the property. And now comes the semantics. I do remember I said the semantics to be a relation on the sequence is not so good. Now I say the semantics of a service with respect to a property is a set of all partners. So I think intuitively it's clear what you say, I have a service. What can I do with what is this? What is its use? Well, it's the set of all. If we together are fine, then you belong to my semantics, and if we don't recognize it, then you don't belong to my semantics. So the semantics is the set of partners with which I can.
But I give you another interpretation. What I am is dependent on people around me. This is stage.
No, it's not. The set of all services should be assumed. It's not that this, but there is a big set of services, and a subset of them is my partners.
So I define myself in terms of the set of my partners.
The semantics of myself. The use of myself.
Okay.
Yeah. I'm useful for my partner. So we should start to think about cooperation. So the definition of semantics is here in terms of cooperation. I am useful as a service because I can nicely cooperate with you and not with you.
And if you don't have any cooperation partners, then you are not.
Then my semantics is the empty set, and I'm a fairly stupid service. Okay. Yeah, so this is mathematically the extreme cases that are not so surprising. You always don't complain if you say only. You also don't complain if you say to multiply by 1 is stupid because it doesn't change anything. You don't complain. You say this is a strange case of multiplication, yes, but it is still multiplication. But you may have a service that is so stupidly done that there's no partners. Still, it is a service, not a very intelligent question. No? This mathematics, maybe it's difficult.
I could follow you, Wolfgang. I tried to bring in a little bit of reality. where you say, I'm only interested in mathematics.
No, I'm not. You will see reality later on. Okay.
Yes, I want to see that, and then I start believing you, not before that.
Wait a moment, wait a moment. Just look into it. I don't believe in clocks anymore. So, there's a classical kind of requirement, say recombination. We have some derived notions, we have seen them already. Substitution of, when can you substitute S by S prime? What is the semantics of S is the subset of S prime? If every partner of S is also partner of S prime. Okay? When are two services equivalent? If they serve the same partners. So this is a very intuitive notion.
But to a certain degree, all what you are doing is you take existing model theory and to apply that, right?
Yeah.
Okay.
Okay. You can adapter. I spoke about adapters already. Now, my last point is, I still have.
I have 15 minutes.
Last point is, what is interesting in composing many services? So far, I was in the theoretical world, we have always considered two services, and we compose them, and then we are happy. And it came to me in the last year that this is by far not enough. We need fundamental questions to answer when you compose many services. And I'll give you, if you like, these concrete examples. This is a supply chain from business informatics. Okay, you start with raw material. This is a server. He runs a service to produce raw material. He is a supplier that takes raw material, gives better material to a manufacturer, and he distributes it. Customer is a stupid word. It means a seller, and you are the customer.
But Wolfgang, here later you need the notion of time. Here later you need the notion of time. So composability is not sufficient because people want to understand what takes place when and so on, isn't it?
Okay. You can put this on top of this. If you want to have a clock, put it on top of this. But start not with everything.
Yeah, that's the difference between Newton's physics and Einstein's physics. He was considering time and then everything looked different.
You see, time, when you speak about physics, time in physics is a very complicated.
I studied it, yes I know.
Yeah. So better avoid to speak about time.
No, that was really years of my life.
Okay, but then at least don't apply this naive, absolutely naive notion of time that we have so far in our everyday practice and think this is an adequate notion to make a theory of services.
Okay, now the only complaint here is not, I'm going to start complaining like Christoph. It's a supply chain. You use a term that many people use completely different. Supply chain really orders what happens, it speaks about inputs and outputs and so on.
Wow. That's a high-level view. That's okay.
So of course they have a lot of things, they communicate a lot of things. And that's what I have in mind. It is not just sending something from here to here, etc. They communicate, but they have to be composed somehow.
Absolutely.
And I come to one aspect of composition which is so fundamental that you will see we have to think about it. And of course, so far we could just say we compose the raw material service with the supplier service, with the manufacturer, etc. So we want to have this chain of this composition. Okay, don't forget this composition because we have assumed a very important stuff here, which is absolutely not trivial. Namely, if you first consider this composition, and then you have a composed system, right, composed system like this, and you compose this system with the manufacturer, then it should be the same as if you first compose the prior manufacturer, and then add the raw material. You see, I've written this sequence, everybody agreed, nobody complained that you should have brackets here.
I was complaining the brackets, so to speak, have been the time that I had in mind.
Yes, that's another story. And to make it even more concrete, so you see we have a socket and an adapter and a British plug-in. I've made this before the Brexit, so now I want to take a different example. Okay, but you see what you usually do, you put in the adapter into the socket, There is the brackets here, and then you put in the plug into the adapter. Of course, you could do it this way. And now you see my point. If you have many services composed, you frequently do it in a sequence, and you always assume that it is irrelevant in which order you compose the parts. But this is not trivial at all. You must make sure this is the case.
So this is why I was asking at the very beginning, what are the laws of computation? Is it commutative, associative, and so on?
Yeah, commutative is not important at all, but associative is fundamental. That's my point here. Okay, again here I didn't write brackets, nobody complained, but you should have complained because it's not trivial that it is associative. I will show you an example later on. Okay, so far now we come back to our algebra. This is our old representation of the algebra, and we now change it. Let's say there is not just a composition operator, but there is an associative composition operator. If it's not associative, it's not useful. Okay? Right. So what we want is a generic notion of service or component such that the service has an interface, an inner part. Two services may compose, may be composed using again a service. The interfaces have some fitting elements, and the fitting element is another aspect. If you fit some elements in the composed service, there are the inner part of the composed service. Okay, and the problem is now find a minimal set of requirements such that services and their composition do what we wanted. Namely, it should be total in the sense whenever you have two services, you can compose them. The result is a service, maybe a stupid one, and it is a service, and it should be associative. That's what we want. How can we achieve this? And let's try. I have a proposal which I think is the first thing you try to do. So we have the service D, then its interfaces A, B, and C. Okay. Now we have a service S, its interfaces A and B. And of course, what you expect is that you put together A and B, and the result is the service, and it's the composition of S and T. And this service has as its interface the C. Now you have a service U, and this service U has a B and a C. And now if you compose this service, then this is the result. So this is the resulting service, which is composed, which has now the structure S composed with T, and the composed system composed with U. Okay, and this composed service has an interface consisting of this V. Now we do it, this is the same starting point, and we do it a little bit different. Maybe first we compose T and U, then is a service which still has A as an interface, and now we compose S and T. And the resulting service, it looks a bit similar because its interface has one interface B. But this is the interface B from the U, and this is the interface B from the S. So these services are not the same. They are different. So this was not associative. Okay? So I have made a very intuitive composition. This is not associative. Frank claims 5 minutes, but I just ignored it. Because we started,
I will pull the plug.
We started 10 minutes late, okay?
Yeah, that's right. You're right. Yes.
I have made.
Okay. Don't talk about time.
I took it such as 5 minutes before the. Yeah. Okay. Now, we must. You see here we have a severe problem. So this naive kind of composition does not function. It is not associative. What can we do? Go to our mama and try to say the word is bad and we cannot solve our problem. There is a very simple, conceptually simple idea, namely the service, the interface of the service may be partitioned in the left and the right part of the service, of the interface. That's what I do now. And we had it anyway, so this service had the left and the right part. And each of these services in the supply chain management had two partners, one there, one there. Not three, not one, but two. Okay? And also here, the adapter has two different sides. So it's very natural that one service has two aspects in this interface. Or for instance, in the classical world, a function in the classical world has an input and an output. The service may have a consumer and a supplier, or a provider and a requester, or producer and consumer, or a buy side and a sell side. So you very frequently have partitioned the interface into two parts. Question?
Does left and right mean causality?
Causality is a difficult notion. Not yet. I just say there are two parts. There are two parts. You see, I want to give you a framework in which you can plug in whatever you want to do. For instance, causality or time or money is money. Whatever you wish you can plug in. But this is the fundamental structure that is present in very, very many cases.
You should also have a concept for doing that for ternary.
No.
No?
I have it for two. Not for one, not for three, but for two. And for two it's enough. For two is at least, for three, four, I tried, I tell you, I failed. Okay. Yesterday we had this swapping pattern, and I thought also it had an original environment and a new environment. I don't know if it's a convincing example, but you always have one thing with the left and the right side. Okay. So let's see if this is associative, and here is a small example of three services. I'll do it now quickly to show you the idea of composition. Namely, this is the right part of S and this is the left part of T. So index right and left. And the idea is to compose the right part of the left service with the left part of the right service. So you compose those two. And this is the right part of T and this is of course the left part of S and of U, and I will show it. Okay, now let's compose them in this way. So you compose the right part of the left service to the left part of the right service, and then you get this, and then you compose it that way, and you get this, and this is the resulting service. So if you do the other way around, first T with U, you get this, and then you put S from the right to this, you get another thing, and they are the same. Believe me, they are exactly the same. So this functions for this example, but not only for this example. So with this simple idea of two parts, you get an associative composition. Of course, I'm cheating a little bit, and I will show you in what sense I was cheating. So I give you another example here. This is a service C1 with this left and right part, and here you have a service C beta with also left and right part, and you see they fit perfectly. There's one C, one D here and one C here, and if you glue them together, you glue them and they become internal structures. And now this is the left part of the composed system, and this is the right part of the composed system.
But again, now Christoph is right, this is context dependent. What are the services that are allowed here? The distinction between left and right depends what services you have available to want to compose, isn't it?
No. Now a service has an interface, and the interface has a left and a right part.
Who is defining what is left and right?
You. As producer of the service, you have an idea what is left and right.
Okay.
You treat your as a business.
But this is like a partial function, right?
Why?
There's the input parameters, which is a V, and then the function creates the output value, right?
I don't speak about input output, but if you have this intuition, then it's okay. Yeah, but it's not only about input output, it's just about plugging it together. It may be discussion in both directions. Okay, I said it is perfect. Did I say perfect? Yeah, they fit perfectly. What does it mean? But you have this D and the C. And now I'll show you examples where we get some problems. Okay, this we have seen already. It's not always that simple because now you see they don't fit perfectly. So C with this C is okay, D with D is okay. But what about this G? G is still in the right part of the left service. What will happen with this? So let's see, you glue them together, and the idea is that the G goes to the right part of the overall system. So this is the resulting surface. Okay. It has a left part and a right part, and what we have seen, the G, which was in the right part of the left surface, now goes to the right part of the compost. Okay? He again announces 5 minutes. So please announce 10 times 5 minutes.
No.
Okay. So this works nicely. For instance, here, let me go back. The C's go together and the G goes over there, and the B goes over there. And the C, this goes together, B goes there. So now we could be happy, but unfortunately this may be the case. And what is here the case? We have an E. So, sorry. At first glance, this seems to the same structure that we saw already, but the fundamental difference is we have an E here, and we also have an E here. And if we compose them, we get a very nasty structure, namely 2 E's in the same part. So here we have 2 E's. And we cannot avoid this. If we want to have a total composition, then we can compose any 2 surfaces. Any 2 surfaces, this can happen. That's the case. So what do we do with this? But that's not so difficult to solve. We must distinguish them.
Renaming.
Okay, you may rename this, then it solves the problem, yeah. But of course, renaming is technically complicated. It is not. If you rename it by A, then there may be a renaming by A. Okay, renaming would be a solution, which is mathematically not so elegant. Much more elegant is my solution. And that is to order them. To say there is a first and a second occurrence of it. And with that, it functions. You know that, right? You can avoid this, and then what you would do is, as I said, here the problem is this C goes with that or with that. That is the fundamental problem. And now they are ordered, and of course this is the first C of L2, and graphically we draw the first elements only always below and the others above. So this is the first one, the second one, okay, always the same one. So this C is due to this another. Okay. So that's a mathematical procedure that is simple, and yours is a bit different. I can stop here, but you will, if you would know what you will miss, then
2 minutes.
I will stop. Get a minute because I don't know the details here. It functions with this concept, and you can prove that this is associative, and the proof took me very much time, but it was not so difficult to prove this. Okay? So these are some details. I think I stop here.
Okay. Thank you very much. Time for 2 questions.
This problem with this double labels, it caused a problem in the naive version. Why don't simply say, if that's the case, they don't fit, so you can't compose them?
Because I want a total operator composition. You could say, in reality, if it happens in your world, then you made a stupid mistake. It's a hint for a mistake. In reality, it should not happen. That is true. But it can happen, and if it happens, that's a hint for you. You may have done some mistake.
Do you have something like a bad service or something where you can map everything on it, like 0 in addition?
I see. I have not thought about this, but this would be an interesting thing to do. Yeah. I have a neutral surface. That means if you compose A with a neutral, you get an A. So this neutral element exists, and there is the smallest neutral. But this is the point. Now you start a little bit farther.
Yes, it's this composition of the surface, and then the inner functions disappear. But in reality, you have the. I think it's different because they are still there, and you have more the problem which one to use. Because
the inner don't disappear.
surfaces are loosely coupled, and the interfaces don't disappear. But I don't know. The meaning is different. I think you mean it's not important anymore because they are using each other. Or what do you mean with this?
So, no, the notion of disappearance is misleading here. So if you compose two components of the interfaces, they don't disappear, but they become inner part of the composed system. They are there, but in the inner. You cannot move in another thing. They are no longer in the interface. They are in the composed system, but not in the
I think what
interface.
he's saying is even if you compose, there may be a service that is sending a message to the same content you just found. You know what I mean?
Yeah.
So this
If you,
some malicious service may send message there.
This is a virtual structure.
Pardon?
It's a virtual structure.
Yes.
So at that context, in that scope, those services are composed, but there might be, in my understanding of it, overlapping compositions or overlaying compositions at the same time.
They are still available, even if they are used by one service, by another one they are available. Normally, but yeah.
not normally,
It's an instance. It's an instance model. In this instance, you can help us about. Let's talk about the final question.
If we have two services with the same label, how do we know they are really the same? For example, they could have the same functionality, but one service would cost twice as much as the other one.
Yeah. So you now put on top of these fundamentals some more notions like cost, like equivalence of differently labeled things and other things. You put it on top of all this. I don't say this solves all the problems. I only say this is the fundamentals on top of which you then start to plug in whatever you need. If you need cost and equivalence, put it on top of this.
Thank you. And to announce